Okay, you are well along your way on learning the rules of derivatives in calculus. We're going to just kind of explore an unusual nook or cranny of the derivative world, and that's when you start getting more letters in your equation than what you really want. I say letters because they're not necessarily always variables. And things like this are going to happen when you apply calculus to the world of physics or chemistry, where you know that you've run into some equations that have way more letters than what you're hoping. So, a little quick review. In this first problem, we have y using x as a variable. So if the question said, hey, what's dy dx? You know that that means find the derivative of equation y that happens to be using variable x. So that's no big deal. But let's now move on to this next equation right here, y equals 4x squared plus w. In this case, I'm going to call w a dummy variable, meaning it looks like a variable, but it's not going to act like a variable, and here's why I know that. The instructions might say find dy dx, which means find the derivative of equation y that happens to be using variable x, which means to your brain, w is not a variable. In fact, w is going to act just like a number. It's say a 17. So now when I do the derivative, this is an x term, so I do the derivative by the power rule just like normal, but this w is not a variable. It's acting like a number. The derivative of a 17 would be a 0. The derivative of a w would be a 0. So you wouldn't even write that plus 0, but I put it in there for dramatic effect. Now in this example, this is the equation y. It's the same equation we were working with, but now the instructions would say, hey, what's dy dw? Which tells you w is a variable. 4x squared is really just a big fancy number, and the derivative of a number is 0. The derivative of a w is a 1. So paying attention to Leibniz's symbolism, even Newton's symbolism, is going to give you some clue on what letters are acting like variables and what letters are acting like numbers. Let's just do some more practice here. This one looks like a little bit of a big ugly. We've got a T, an A, a V, and a W, but the symbolism tells us it's equation P that happens to be using variable T, so I know A, V, and W are just like numbers. If I felt like it, I could rewrite this like this, 3t to the 5th over 7t minus 4 times 6, which would be 24. So you could rewrite it that way. It's probably going to make things more complicated, but that's definitely the way you should think about it. So now if I need to find dp dt, I know I've got quotient rule, and here we go. Sing the song to yourself. Low d high minus high d low, all over denominator squared. And here is my low. Don't do anything to it. The derivative of the top minus the top times the derivative of the low, or the denominator. Now here's where we have to think. If I'm taking the derivative of this denominator, this is kind of acting like a 8t. The derivative of 8t would be 8, so the derivative of at is a. V times w, that's just a number. The derivative of just a number is a 0. So when I do the derivative of the low, it's really just a. This whole thing probably would just write as an a, all over denominator squared. So this is a big ugly mess, and maybe you could simplify it and make it look better, but really this is a correct derivative. Dummy variables in this case were the a, the v, and the w because they acted like numbers. Let's do another one. Okay. Another quotient rule situation, and I have equation J, x, w, and v. By this symbolism, I know v is a variable, which makes x and w a number. If I'm asked for dj dv, I could do quotient rule, but there's also an eyeball adjustment that you can make if it helps you. Most people would prefer power rule over quotient rule, so I could rewrite this using the algebra property that says if you move something from one part of a fraction to the other part of the fraction, you just change the sign on the exponent. Now, having done that eyeball adjustment, I can just go ahead and do power rule. Exponent times coefficient, lower the exponent by 1. Boom. Same equation. Now we're going to look at it one different way. What if we were asked for dj dw? That means w is your variable. So I might think of it this way. Where x over v squared acts like a coefficient, since those are all numbers, this is kind of like j equals 7w. The derivative of 7w would be 7, so the derivative of x over v squared w would be x over v squared. So you've really learned nothing new in this miniature lesson, but what you have learned is that your rules of derivatives combined with your knowledge of the symbolism have to work together in situations where you have formulas or equations with plenty of possible letters or variables. See ya.